Good morning, and thank you for joining us this morning for the SCTE Gateway Chapter presentation, fiber troubleshooting. Quickly here, just a little bit about the SCTE. If you're not a member, reach out to your supervisors, reach out to myself, Hunter, anyone that you've got contact with that's in the SCTE can facilitate you becoming a member. Some of the great things about SCTE are these trainings that we do every month. We are presenting it live here in the room for several individuals as well as the live stream today. So hopefully you're benefiting from this content. If there's things that you'd like to see that we're not training you on, let us know, please, and we can help facilitate that. I am Dennis Russell with the Gateway Chapter Board. We do these every month, and the other great things about SCTE are the live events like Cable Tech Expo. We are doing a mini version, local version of that here in May. It'll be on May 15th. What happens at that event is several vendors from across the country will converge on St. Louis, bring their latest and greatest products, tools, equipment, technology for everyone to kind of see and put their hands on, as well as we will facilitate a local Cable Tech Games. What will happen in that is 7 individual events where people will compete Olympic style for medals and bragging rights, and ultimately a trip to Expo this year in Washington, D.C. to compete on the big stage. So a few of the guys here in the room have done that. It's a very cool experience, and it enables you to network and meet individuals from across the world that can facilitate training and all kinds of help and information for you as a technician on any level with the gear that you use, the technology you're using every day. It's one of the most valuable parts of the SCT to me, is being able to reach out to individuals such as Steven here to ask him questions and find out how his gear works and make sure I'm using it to the fullest potential out in the field. The other thing about the SCT is certifications and trainings. The trainings and certifications that you can receive through SCTE are nationwide, actually worldwide. They're recognized by all companies within our industry, and that's stuff that people cannot take away from you, is the learning and education that you can receive through the SCTE. Recently, one of our members, Andrew Vance, part of the Gateway Chapter, has received his BFTCS, broadband fiber specialist, and his BTCS, his telecom center specialist. So congratulations to Andrew. He's using his membership to the fullest and gaining a lot of knowledge that's going to help him in his daily career and help him move up that rung to the next rung of the ladder. So with that, appreciate everybody being here. And if you do have questions about the SCTE, please reach out. We're going to go ahead and get started this morning. Steven with Ervin Construction.
Let me steal the mic from you real quick before we do that. I apologize. I should have said this up front. So for everybody that's on the live stream, apologize for it being so clunky. We're learning as we go. That's what you get when it's a volunteer organization. Everybody that's on the Zoom call in the top right-hand corner, you should have view settings or something similar. If you go to speaker view, it'll give you the big window of Steven and what he's presenting. And then when we screen share in, it'll hopefully present that for you. You may have to play with gallery view, speaker view, grid view. But to get the best experience, I think you want to be on speaker view for the majority of the time, and we'll figure it out as we go. So if you have questions, there's a chat room with this Zoom meeting. Just post your questions in the chat room. If you accidentally unmute, I'm going to mute you so we can manage the background noise in the chatter. But yeah, pose as many questions as you want in the chat room. We encourage it. Apologies for not saying that up front. I should have caught Dennis before we did that. That's my fault, guys. Good.
Good to go.
Steven, it's all you.
Thank you, sir.
Good morning, gentlemen, and everyone on the live stream. My name is Steven Hudson. I am a certified FOA instructor with the Fiber Optic Academy, and as well as that, I work as the splicing supervisor at Ervin Cable Construction. I'm currently helping to manage the Fiber to the Home project for the Indiana market. I started my path in fiber in 1994, so I've been doing this almost 30 plus years. Started right out of high school, and been teaching for the FOA since about 2012. I teach basic fiber all the way up to advanced, and then get into theory, talk about how to troubleshoot, how to identify issues on fiber to the home networks, premise networks, and long distance networks, and so forth. I do not know everything about fiber, so if I don't know and you do ask a question, I'm just going to say I don't know. All right, I do have quite a bit of experience, and if I do know, I'm obviously going to share that with you today. Today, we're going to get into, basically, we're going to talk about troubleshooting with OTDRs. We're going to discuss why you use the OTDR, what its application is for, the troubleshooting portion of the OTDR and how to actually identify problems, short distance and long distance. We're going to talk a little bit about the theory, kind of how it works. I want you to understand how the system actually works so you'll be able to interpret the information a little bit better. I will take you through how to make settings changes, and we'll kind of get into what happens when you make a settings change. Does it change the trace to where it looks a little different to you and you're not able to analyze the anomalies on the fiber cable? And we'll just kind of go through all of that. We're going to test through a bare fiber spool. It's about 7 kilometers of fiber. I'm going to test through that. I'm using a launch cable, a homemade launch cable that I made myself. It has both APC ends and regular PC ends, so I can test multiple networks. We'll go all the way through that. We'll kind of talk about why it's important to use a launch cable whenever testing networks. And on the way here, I was talking to some of my guys about some troubleshooting issues that they had in a hub. I will probably go ahead and kind of talk about what we deal with every day, which maybe, is that me? Oh, too. There you go. There's our first good one. That's it. Now we're through. All right. Broke that ice. So anyways, I'm probably going to reach into my own toolbox of what we've been doing in Indiana. So I'll give examples of some of the issues that we've experienced, and and maybe you'll be able to relate to, all right, yeah, I've kind of seen that. I've had that issue. We're going to talk about just the basic level of the OTDR and just try to understand really what its purpose is. So I'm not really going to qualify myself any more than that. We'll just jump right into this material. So for anyone that does not know, turn off your phones. I knew that was going to be me, and it was Bob. What about Bob? It's a good movie. OTDR, if you don't know this, a lot of guys don't even know what it stands for, don't even know how it works, don't even know what it does. OTDR stands for Optical Time Domain Reflectometer. All right, most of you guys probably never knew that and really don't care. But what I do want to talk about is how it actually operates. It uses optical pulses of light. It averages that light that it sends out over time. And it's always checking reflection. It's its main job. OTDRs use what's known as back reflection. You didn't know that. It's called backscattering. So as we send a pulse of light down the fiber, as you see on the screen here, the pulses of light continue down the fiber, and every event that they come to, the light bounces off of that event and goes back to the source. Comes back to the OTDR. Having said that, the way that a majority of these work is they always test from one end of the cable. You generally test from one end or the other. You may use 2 machines to isolate an issue, but this piece of equipment only shoots light from one side of the fiber. So as it sends the light down the fiber, you'll see how it interacts with different portions of the fiber. That light returns back and goes through a little splitter inside the OTDR and then goes into what's known as an avalanche photodiode. The avalanche photodiode on these machines is different than regular diodes that you use in your everyday world. When it says avalanche photodiode, you can think of it real simple. It doesn't take a lot of sound waves to cause an avalanche. Make sense? Doesn't take a lot of light, electrons returning back to this machine for it to pick up, kind of analyze, and determine what's going on the machine. Now, right now, I'm running this in live mode. I'm sure most of you guys have probably used live mode, possibly. I'm sure you use this to troubleshoot. Some do, some may not. Most people probably use this in basically what's known as full auto mode. In auto mode, the machine pretty much does everything for you. I'm going to show you today how we can do settings changes to get more accurate information. Dial the machine in. So right now it's in auto mode and it's sitting here constantly pulsing, and that avalanche photodiode is receiving all of that light back into the main unit, coming all the way back to the source. The source being right here, the very first connection. No problem. Yeah, work. Yeah, because I do want you to see this. Now look, this is a standard trace. They all look the same. I'm using a personal machine because we're still having technical difficulties with the Expo. Most of you are probably using Expos. It's all right if I ask the guys in the room a question. Is this correct? We can interact. Yeah, so just know I'm going to talk to you and you're going to talk back to me. So that's why I'm looking you right in the eye, because we're the ones talking. I don't know about these other people. Do you use Expo? What kind of machines are you using? Do you know? Viavis, all right, very good. So JDSU makes a version. This is right here. This is an OWL, Optical Wavelength Laboratories. They're all similar in their principles and how they work. So when we do make settings changes, the only difference is you'll have to learn your machine when you go back and work with it. Okay? So first thing that I wanted to tell you guys, and just kind of take it very basic, all right? When I go in and I teach OTDR, I'm trying to teach someone who's never actually used it yet. You need to understand what it's there for. The OTDR is used for troubleshooting. Its main objective is to help you to identify issues. And how does it do that? Well, if it sends out pulses of lights here, then what it actually operates like is radar. So it's going to send constantly pulse. As it finds an event, the light bounces off that event, goes back to the source. So it's constantly averaging. It's always got to do a round trip. Light's got to get all the way to the end as far as it can go before it returns back to the unit for the machine to actually analyze what's going on. So having said that, we've got to actually understand, with it working as radar, we got to make sure that we use the right pulse widths, and we want to make sure we use the right settings, how many times we average. Averaging is basically what they call sampling. Sampling is how many pulses you send out. We also need to do a setting to actually determine the length of the cable. So whenever you're testing a long distance link, you're going to have to make sure that you set the distance on the unit to be at least twice the distance of what your cable is. Now, the first question guys ask me when I tell them that is they say, well, if I don't know how long my cable is, I'm working in the field and I don't have proper documentation, so I don't truly know how long fiber is, then I generally tell them, well, you can run the machine in full auto and let it determine the actual distance. So we're going to learn a little bit about that and learn about changing pulse widths. We're going to learn about changing the distance. Always twice the length of the cable. So we're going to do that. And as I make these settings changes, you'll actually get to see it live on the machine here. That's why I like to run in live mode, so you can actually see that settings change as we go. We'll also then try to test through, we're going to test through this spool of cable and do some troubleshooting on that spool of cable. I'm going to show you what APC connections look like. I'm going to show you what standard PC connections look like. You need to know what APCs look like so that you can actually determine if you have a good or a bad connection. So in our world, we go from the central office, the CO, we shoot light down from the CO. We're always testing all the way to the hub. We're trying to check our feeder routes. Is everybody with me? All right, this is all terms that I'm sure you already know. And when we're checking the feeder route, we're trying to check to see that we have continuity all the way to our hub. So the very last thing we're going to see on the hub is back reflection, because it's plugged into a splitter. Now, this is just one that I take around in class just to display, but this is a 1x32 splitter. Same thing that's inside your cabinets. You guys are probably familiar with these. You've had to plug these, you snap them into the configuration in your panels, whatever you use in Clearfield or CommScope. I don't know what you guys are using, but we use Clearfield in our market. So we'll actually see what that looks like. So you can actually see what APCs look like, because you'll always see back reflection. So as we go through this, we'll kind of talk about these changes, the settings changes. We'll kind of see how they change, what's different in them. And we'll dial this machine in. We'll use it in full auto, plus we'll dial it in to see how it operates. Now, number one, if the OTDR only checks from one end of the cable, then it doesn't truly do what's known as an insertion loss test. So everyone that's on the live stream and everyone that's here in the room, a majority of you should know what an insertion loss test is. This is your optical loss test set. Do I get to go to the second board, did you say? Your OLTS. All right, your optical loss test set is your light source and your power meter. Do you guys certify your networks by doing a bidirectional test from your central office down to your panels, your patch panels and your hubs? You should be, okay? When you go from the hub, which is known as the F2 side, the field side, you do the same test. You do an optical loss test set. That means that you have a source that is constantly sending a pulse of light down the fiber. You have a receiver that's receiving that signal. It is simulating how the user will operate when we plug them in to the equipment. The OTDR operates in a very different way. With the OTDR, it's single direction testing. As we said earlier, it operates like radar. It only shoots from one end of the cable. Therefore, there is nothing at the far end that's actually receiving any light. And here's why I like to stress this. You cannot use the OTDR to certify a network. There's a lot of companies that believe you can. And it's my opinion and CFOA's opinion. I stick with policies and procedures, not really my opinion. The process, the use of the OTDR is to locate events, finds a fault. It can tell me what's wrong with a splice. It's the only thing that can tell me individual splice losses. It can tell me back reflection. It can tell me how much reflection is happening across connections. It can tell me the length of the cable. Now, I'll know a lot of guys will say, well, I have a machine. My OLTS tells me all of that and tells me the length of the cable. Well, that's great. But you just need to understand what the purpose of the OTDR is. So having said that, the way that we use the OTDR is basically just to try to find whatever our issues are on the cable. Now, as we continue to go into doing the different settings changes, we'll also talk about how these work. They operate in different wavelengths. A lot of these units will do dual wavelengths because a lot of the systems that you operate in are going to operate in at least 2, maybe 3 separate wavelengths, what's known as wavelength division multiplexing. Very simple. If you've worked in fiber long enough, you already know in the single mode world, use 1310. You will probably see 1490. You'll see 1550 nanometer wavelength. You guys know all this? You shake your head if you do. I'm talking to you guys. All right. So the way that we test is the OTDR is always testing at a certain wavelength. Well, wavelength's very simple. It's the color of the light. It's the speed at which the light is traveling through material. Every wavelength is a different color. And it's very simple. Whenever we're referring to wavelength, we're literally talking about electric wave and magnetic wave traveling over distance in time. And so when they say wavelength, they're measuring the distance between those two wavelengths. So let's say that's 1310. Now, I don't want to go too deep into the weeds, but if you're going to measure it accurately, you got to put it in a unit of measurement known as a nanometer. That's a billionth of a meter. That's how small the unit of measurement is for these wavelengths. So for most of our systems in here, we do multiple wavelengths. So you have to do wavelength testing as well. 13 nanometers. You will see a 1490 nanometers. You will see a 1550 nanometers. And each one of those transmits different data simultaneously. Now, if you didn't know this, the systems that we're working with, well, let me back up and say this. Why is it important to do bidirectional testing over your networks? Well, you didn't know this. We use one single fiber to send multiple signals to each user passively. This is a passive optical device. You guys work with PONs, passive optical networks. This device right here takes one single input. Where can I display this? You want to come hold this for me there? My man. If you didn't know this, and like once again, I'm just taking this very basic just so everyone kind of is on the same page here. I got to hold this just right. This is pitiful. Listen, here's a plug for buying cheap equipment. Okay? You buy cheap Chinese stuff, you get what you pay for. All right? If I'm in trouble for that, I apologize. There's got to be a disclaimer on the screen that says I don't know anything about it. So this is a 1x32 splitter. The way that this works is it takes the individual signal. Are we able to see that light? Is that coming through at all? All right? And it takes that signal and it splits it 32 ways through one single input. Are you seeing it? Is it blinking? Barely. It's coming on and off. All right. Thank you, brother. So what's the purpose of that? Well, with the passive optical network systems, we're able to use, like in most of your hubs, I don't know how your network's configured here, we use 12 fibers to light a hub, or we may use 18. All right, we use 12 fibers to light a hub if it's a 288. We use 18 if it's a 432 cabinet. Those 12 fibers, we generally only send 3 signals out, and we light 3 to 4 splitters, 5, maybe 6, who knows. We never fill a complete cabinet. You probably already know all this. Okay, this is all very basic stuff. Those signals that we send from the central office broadcast to everyone. And then at the home, you guys have what's known as a network interface device, a NID. The NID at the home has an IP address that picks up that signal, and it gets whatever traffic that it wants to receive over these wavelengths so you can communicate. So 1310 is what we call our upstream communication. All right, 1490 and 1550 are downstream. I'm going to shorten that. And we actually do voice and data across 1490, and we send video across 1550. There's a reason for this. The upstream communication, since it's 1310, is traveling at a slower rate of speed, so it actually doesn't go as far and doesn't travel as fast, but it's carrying data, bits, ones and zeros. When you're pushing voice and then you're receiving data as well, you need to go at a longer wavelength. When you're doing video, you've got to go at pretty much the longest wavelength to get the best signal quality to the end user. All this happens passively and simultaneously. That is wavelength division multiplexing. It's that simple. So having said that, that's why we test with the OTDR at multiple wavelengths. Now, the machine that you're seeing right now that I'm sharing on the screen, we're only testing at 1310. That's simply because the unit that I have really only tests in 1310. Generally speaking, you probably are using a system that does both 1310 and 1550. Now, this machine that we have here that Ervin has provided is an FTB2. It actually is able to do 5 or 6 different wavelengths. And then at the network in Indiana, we actually use a specific wavelength to test. All right, so the bottom line is when you set up your equipment, you need to make sure that you're using the proper wavelength and the proper settings when you're testing your network. Gives you accurate information. So we'll actually set that up as well. And then, and as much as I will probably set up on my machine, is I'll actually take you through and do the settings changes on here, and we'll go through and talk about what we're looking at. All right, so another thing that we have to pay attention to with the OTDR is you've got to pay attention to whatever the index of refraction is on the cable. Now, without going terribly into the weeds, the OTDR actually can determine what the index of refraction is, but it's very simple. It's a very simple term. It seems complicated, but it is not. Index of refraction is the speed at which light travels through material. Light traveling through air travels at a different speed. Light traveling through water travels at a different speed. The environment changes. There's different, there's water molecules in the air, there's dirt, debris, the clouds, whatever. Light's always changing as it enters a different medium. So when you're testing with the OTDR, you need to know what the index of refraction is for most of these cables. Once again, I'm giving you all this information so you understand what you're dealing with. Here's the good news. You can run the machine in full auto. You don't have to worry. But if you truly want to dial down and you want to get very granular, then it's good to know all of this information. So we'll talk about the index of refraction. This one right here says that currently it's set to 1.4672. There's a whole math equation. You can go through and look at that to determine what each cable is. The manufacturer usually specifies that. But let me ask a question. How many people test the fiber on the spool before they install it, either aerial or underground? How many people have actually tested the fiber on the spool? Thank you for answering. Yeah. So I'm sort of assisting on a project. I never sleep and I'm a workaholic, so all I do is work. And so I'm going to help with some projects on the side, just to continue my skills. And before we actually put the cable in the ground, we're going to do what's known as a live fiber test across bare fiber. So when I talk about making sure we know what the index of refraction is, normally if you go out to the spool in the yard, you'll actually see it should be written on there, but it may not be, okay? If it's not, as I said at the beginning, you can always run this in full auto. The machine will determine that itself. So some of the main things that the OTDR does, besides changing the actual settings, what can it do? Well, number one, it can tell me the length of the cable. It can determine distance. When set with the proper settings, I can find out how long the cable actually is. I can determine where the break is. It can tell me actual splice loss. All right, and we'll actually see how you do splice loss here in a second. Determine actual individual splice losses. It can tell me back reflection. My spelling is terrible, so please bear with me. It can actually do what's known as a fiber characterization. I'm probably going to spell this wrong. That's wrong. Good. It's hard to spell in front of people. Try doing math. Try doing math in front of people. You're sitting here going, 1 plus 1. 1. So it's a joke. Come on, laugh. Come on, guys. Lighten up. You are not the one that's on the screen right now. Chill out. The last thing that it can actually tell you is it can shoot. It's able to determine if there's any kind of dispersion that's on the cable. Now, I'm not going to get too deep into the weeds with that, but with single mode fiber, there's a couple of things that we do need to be worried about with single mode. Number one, we do have to worry about what's known as chromatic dispersion. The root word of chromatic is chromos. What does that mean? Color. Just means that when you get a far enough distance away from your light source, the light slows in its speed. This is very simple. Just think about, parking lot. Last night, you were driving home from work, you were in the parking lot, you saw a light over in the corner of the parking lot, halogen light, whatever, LED bulb, and that light, as it slowly came to you, it changed in its speed, it changed in its color possibly, and by the time it got to you, it was less energy from where it started to where it got down to the end. So same thing happens with light sources. In some of the markets that I've worked in with Ervin in southern states, we actually reuse fiber over and over and over again. And we go up to 200,000 feet plus to get out to the rural area. So when we get out that far, the light might have a little bit of an issue just because it's dissipated. It's lost its energy over time. So it'll actually check for different types of dispersion. And then the last thing that the OTDR checks for is what's known as polarization mode dispersion. So I always tell students that come through my class, I want you to be smarter than the average installer. One thing you need to know is single mode fiber is what's known as a stepped index fiber. That means it has one layer of cladding. And you guys should know this. If you don't know this yet, then I hate that for you. Whoever you're working with needs to explain these things to you so you know what you're dealing with. It's got one layer of cladding, one layer of core. Core is about 9 microns. It can be anywhere between 8 microns and 10 microns. Very small. When it means stepped index, it just means that there's only one layer of cladding and one layer of core, and the light is the core is so small, so tiny, that the light only has one choice but to go straight. It goes in a straight line, hence the word single mode. Single mode fiber only carries one mode, so the light goes further. Imagine this. You can go up to 100 kilometers with single mode fiber before you actually have to amplify the signal. So, as it being a stepped index fiber, there's a couple of things that we need to worry about. And this will kind of blow your mind, but when fiber is produced, yes, the core needs to be absolutely perfect, but its concentricity may have changed. It may not always be a perfect sphere or circle. So the core may have changed. When the core does change, then it causes problems in the fiber. You'll see loss. So we actually have to worry about a little area all the way around the fiber known as the mode field diameter. So you've got your main core, and then you've got a little bit area around the side. You have to worry about the mode field diameter. So having said that, what's the reason that we worry about this? Well, the OTDR is the only piece of equipment that can test to prove if there's something wrong with that. That's when it gets into characterization. Now we're talking very long distances at this point. Now we're going 60 to 100 kilometers. We're traveling from city to city or whatever. So that's what is entailed in the characterization portion of the OTDR. Now, I started all of this to say the OTDR cannot certify a network, and a lot of people seem to believe that. It cannot do that. Its main objective, as I said, is to find the faults and the issues. So we're going to go ahead and jump in to see if we can find a couple of faults and issues here, and then go through and do a few settings changes. All right, so my screen is being shared at this point. Good. Thank you, Jake. My driver, Captain, my captain. All right, so number one, right now we're sitting in live mode. Let's go ahead and jump in and start doing a couple of settings changes. Let's go through and talk about the different ones. Now, here's the bad part. You're not gonna be able to see what I'm gonna change. You're not gonna see the settings that I'm actually gonna change. I'm really gonna have to stop this whole system and then restart it again. So I'm gonna close down this application. I don't know. Probably, yeah, it'd just be easier. It's just rude of me to say, hey, do this. That's very rude. So right now, let's just go very basic. Let's talk about it. So on the OTDR, you see your screen. It gives you a graphical representation. Have you ever thought how it actually works? It's kind of amazing if you think about it. It allows you to take a snapshot of the fiber so you can see graphically what's happening. It's a fairly amazing process. So having said that, you always are measuring a certain amount of loss. Say again. There we go. All right, so there is my loss scale. After that, you have your distance scale. Now, I know that everyone in here does not like using the metric system, but the way that we actually measure fiber, because it's got very minute and small sizes, is we're going to measure everything in the metric system. So the standard that we use to actually test with checks everything in feet, kilometers, meters, but it doesn't check anything in feet. Yeah, and mine is set right now in meters. Now, the main reason for that is the way the standards are configured. You would have to do the conversion of feet to meters, and then you'd have to multiply your distance and your loss and figure out what your values are. Now, I already know what everyone does. They go into the machine and they change it to kilofeet or feet or whatever. They do not use the meters. Anyone want to correct me if I'm wrong? Am I wrong about that? Speak up. Huh? Good Lord, like the cat that ate the canary. They're all looking at me like, I don't do that. No, I don't do that at all. No, sirree. Yeah, well, I am not going to curse on television. Here we go. So everything we do will be actually in the metric system. All of the OTDR trace, known as a trace, and probably you guys know it as traces. All this information is very valuable to us. Now, right now, this one is sitting, as I said, in live mode. It's constantly pulsing. All right. The neat thing about doing the live mode that we like to do, I'm going to open up my homemade launch cable. I'm going to see if I'm hitting the right fiber. If you guys ever had to troubleshoot and you go out and put micro bins in your fiber to actually locate bad splices? Yes? No? Maybe? Sometimes? Okay. It's a very handy troubleshooting tool. It allows us to actually determine right where we are on the fiber. I am not finding it right now, so I'll just bypass that for a minute. I'm not going to get messed up about that. But the main reason the live mode works, as you constantly pulse, you can actually see and mark exactly where your problems are with your fiber. So I'll give you an example. We had an issue, and I wasn't actually out testing, but I was talking to some guys that were testing yesterday. And they had issues in what they believed was in a case that was inside the central office. Well, you worked in fiber long enough, you do not want to mess with live fiber, okay? You don't go in and open up a case in the central office unless you know what you're doing. And so they went in and were actually trying to check to see where the issues were. And one of the tools that, we're able to use is we can go in and find the fiber pairs that we want to work with. We can put a little micro bin. We can determine if that's actually where the issue is. So it's a very handy tool. So we use live fiber mode quite often. We'll go in and change the pulse width. We will leave the wavelength the same. I will change the number of averages, and then I will set the actual distance of the cable. And we'll see if we can see this whole network. Now, like I told you, this is 7 kilometers of fiber. It's 21,000 feet. So right now, am I really seeing a full 21,000 feet? Well, let's just go straight to the trace. We're going to our sample trace here that we're looking at. And as you can see, we have whatever amount of loss we see on the left-hand side, and then we have our distance, and then we see a reflective peak at what, 210 or 207, 214. You see this? You see all these down here? You see these events? There's my reflective events. So there's a connection there. It shows reflection. We're going to get into what's good and bad when it comes down to reflection. It's kind of it's an interesting animal. With reflection, the higher the negative value, the less reflection. The lower the negative value, the closer you get to 0, you have more reflection. So generally speaking, when we see reflection, we want to see a neg 40 or lower, which kind of is, in your mind kind of throws you off because loss is inverse to that. So we want to see a reflective peak that is fairly low, and it is saying the reflectivity is negative 42.52, fairly decent. Says the loss is 0.43, fairly decent losses there. Goes into a non-reflective section at 277, another non-reflective at 306. Shows a reflective peak at 400, and then says reflective in at 442. So are we seeing 21,000 feet? No, we are not. I'm going to have to change some settings. Now, I personally do this to kind of teach. Now, I really am sorry that I'm going to have to stop this because it's going to stop. We're going to restart it. But I'll have to go in and make the settings changes. Now, what I'm going to do is I'm going to go and run this in full auto. In full auto, then you'll see what normally you guys would see when you're out in the field. Generally speaking, what you guys will do. So I'm going to have to stop this application. Actually, I'll just stop it here. In full auto, I'm going to have to do the trace, save the results, download it. It's the only issue that's going to happen here, so bear with me as we do this each time. And then we're going to talk about the different components. Now, are you guys using launch cables? Good answer. What is the minimum length of launch cable that you're using? 1,600 feet? Very good. So, in theory, you need around 700 to 1,000 feet for the pulse of light to actually go through a section of fiber and calm down. It's known, a launch cable is known as a pulse suppressor. It makes sure that the first connection and whatever you're testing that's right there next to the OTDR, I can actually see it. Because with the amount of power that we're referring to with these OTDRs, if you send a pulse width that's that strong that's needed to get to the end of the cable, it's going to blow right past that event and does what's known as saturate the actual connection. So you should always use a launch cable. You need to know the length of the launch cable. So a lot of questions I'll get from guys is, well, if I don't know the length of the launch cable, what can I do? Run your machine in live mode. Just plug in the launch cable. Then you'll get the light will jump in and it'll come to the very first connection. The very first connection is going to have a flat top. It's going to be saturated. It's got an area known as the dead zone. That dead zone is the very first connection plugged up to the OTDR. You cannot analyze that connector, so just forget it. So you never do that. But if we're trying to check the length of our launch cable, it'd go down and then you'd see another reflective peak and then it would drop off and it goes into what we call software noise world. Well, if you want to measure the length of your launch cable, then you put a cursor out here on one side, another cursor over here, and you can get a distance between these two. Then you can plug that into your OTDR. Other OTDRs will allow you to make a settings change that says not disconnect, but discount, or the word I'm looking for is like it bypasses. It looks at the first connection. It says, look, don't even worry about the first connection. Check the next connection. So the next connection will be your next connection in from the launch, because here's my first connector. Then I have my second connector. Make sense? So it's very important to set your OTDR launch cable lengths at the proper length, so that you can determine what your network is. Now, the next thing that's important about the launch cable, if anyone, be honest too, who uses a receive cable? It's just a glorified launch cable. Do you put a launch cable on the far end? How do you know the loss at the far end? What is that? That's my house. You weren't supposed to see that. You're not supposed to know where I live. Do you put a receive cable on? No, you do not. How do you know the far end connection? How do you know the loss across the far end connection? How can you? When the light gets to the far end connection, it has to go into another connector for you to actually see the loss. So if you don't put on a receive cable, you really don't know the far end connection's losses. Does that make sense? Are you tracking with me? Now, here's another reason why it's nice to use a known launch and receive cable. You ever get into when you're testing networks and you're having some major issues trying to find out the actual length of your segment? Well, wouldn't it be nice to have a known good distance at the front and at the end? And then all you got to do is just subtract those two distances and you know everything in between is the actual cable. Why is that important when I'm trying to find a break? Now, I always refer to, I go back into my own toolbox. We've had quite a few fiber breaks, what we call backhoe fade. All right, we've had guys set anchors. You ever had anybody set an anchor? Do a down guy, punch right through your pipe, screw your fiber right to the ground. You ever had that happen? I mean, surely you have. It's happened to me. It's happened to you. All right. We had that happen on a 288 fiber in a city in Indiana, and we're trying to find out where the issue is. So instead of using a launch and a receive cable, really what we did at that point in time is we used two OTDRs. And I went from one end and I shot the far end back toward the hub. My technician went to the hub and shot from the head end back toward the far end. We were able to get a general location of where the break was. And lo and behold, doing that technique, we went straight out there and walked right out there and looked at the pole and saw a brand new down guy. And do you think they told us they did it? No. Do you know what they did? Can I tell you a secret? Don't tell anybody. So can I tell this secret? So they dug a hole and they used a sawzall and they cut off the top of the anchor, the rod. This is how smart these guys were. And they didn't destroy evidence, so they just left that in the hole and the sawzall blade. And then they just moved over and they set another anchor right next to it. And when we asked them, we said, do you guys know anything about it? No. Do that. Yeah. So objective, main objective to reason for this story. If you have a known good launch cable length, a known good receive cable length, it helps you to determine the problems a lot faster. All right. If you can't do that, then you obviously use two machines, shoot from both ends, whatever. So we're going to go through and check all of that. All right. Now I am going to download this trace in full auto, show you what it looks like, and let's see what looks different about it. You tell me if you notice the change. Yes, I know that date is wrong. Bear with me. This is just informational. All right, going into the basics of OTDR. How? Uh-oh, am I still doing something wrong? You're driving. Drive for me, brother. So, how do you actually analyze a trace? Go ahead. I'm waiting on you. Oh, I see what I got to do there. Thank you. How do you analyze a trace? Right? You shot light across the fiber, trying to determine the length, trying to determine your problems. You're trying to find out where your issues are. What do? Use cursors, right? Markers. Left, right, 1, 2, A, B. In my world, mine are red and green. I am able to determine distance and loss just by moving these cursors. Now, you can see we need this minimized. Can I just do that? All right, I just did. All right, I need to do this right here. This just needs to go away. Thank you. Go right there. You live right there. What's the distance between the left and the right cursors? The left cursor is 31. What does that say there? Anybody read it to me? It's 3, 1, 4, 6, 7. What's the other one? 7, 1, 8. All right, so 7, 1, 8, 3. So it believes that the difference between the two is around 7,000 meters. All right, so, if we're going to go back and we're going to do math, I told you it's really hard to do math in front of people. But if you've got 7,000 meters, well, there's 1,000 meters in every kilometer. In 1 kilometer. All right. So if you're going to figure out what 7,000 meters is in a kilometer, you take your decimal point, you go 1, 2, 3. Real simple. That's 7 kilometers. So we found the end of the fiber. I'm happy. Are you happy? I'm happy. Because that's the biggest objective. You don't find the end of the fiber. You don't find all the anomalies on the fiber itself. You don't find anomalies on all the segments. What is the purpose of anything you're doing? Give you an example. Testing a network this summer, we had a good plan, schematic, whatever you want to call it, print. Okay. According to the print, as you follow the main line down to the hub, about 2,000 feet. But as we shot the OTDR trace, we were at 4,000 feet. We had a little discrepancy there. Now, we finally had to find out that someone had flopped some fibers and flipped some stuff around, and they'd pulled from the wrong tube, and so the light was going a longer distance to get down to the actual hub. But that was a very important exercise because we had good light. Could have left the hub hooked up that way, but it wasn't per design. It wasn't the way the print had designed it. So actually knowing the distance, pretty important. Obviously, if you don't have a good print, you really won't know the distance. That's going to be another issue altogether. Okay. So at that point, you're just kind of blind. So we found the end of the fiber. It says it used a pulse width of 500 nanoseconds. It did a number of averages. That's the sampling rate, did 4,096 averages on the sampling rate. And it actually gave a trace length of about 9,808 meters. Main reason for this is it believes there's some sort of reflection that's happening at the end. Have you ever heard of a ghost, a reflective event at the far end of the cable? Have you ever seen it? Okay, so let's look at a trace. Let's look at this trace. Let's straight analyze this one. Number one, I told you we always use a launch cable at the very beginning. So the actual launch cable itself, I didn't predetermine the length, right? I didn't go through all that, but you just saw it on the trace. Well, that launch cable had a reflective peak right here, then it dropped down and it came up and it had another event right here in reflection, and then it went into the fiber. This was my dead zone. Then we had a reflective peak at the end, and then it dropped off down here into software noise. When we moved our cursors out there, we determined that this was 7 kilometers, the distance between here and here. Well, that was my launch cable up here at the very beginning. So some machines will actually just gray this out and black this out, and you don't actually even see this event at all. And it will just start at the very first event. Now, the importance to knowing how and where to set the cursors and the markers as you're actually doing this is the following. This is my launch cable, this is my distance of fiber. This area right here, we already said was my dead zone. This is going to be a tough question, but I'm pretty sure you can answer it. Where do I want to put my cursors to actually judge loss and distance? Well, if this is my first mated pair, this is a connection. This is this one right here. Then if I'm going to judge the loss across that and the distance, then I actually got to put the cursor on the left side. Do you agree with that? You have to. Because you want to go ahead and measure that first connection, because you need to know how much loss is happening across that first one just to determine if it's dirty, mated pair issue, you didn't fully seat these properly, whatever. Now, earlier I asked you, I said, can you actually measure the loss across a far end connector? Here's my far end connector. Can I measure loss across that far end connector? Not unless I put another connection out there. So I have to put the cursor on the left-hand side of this actual connection on the end, because if I move it over here, where am I at? I'm off in software noise land. I'm in nowhere land, because this is the end of the fiber. So you got to pay attention to where your cursors are. Now, the reason that I like to point this out, and it's just me personally, once again, I go back to my original toolbox of issues that I've dealt with. When we light up these hubs, we know there's back reflection at the very end at the hub itself, the connections into the actual splitters, but we don't generally worry about the loss there. It's very strange, and I do not know why. This is, once again, this is a policy, it's procedure, it's a thing that you should do, but if I don't worry about the reflection at the far end, then when I go to hook up that hub and I get light to that hub, it's going to cause an amount of loss that's unacceptable. Let's go to an example. We were testing the network at the end of the summer, and every time we plugged into a splitter, we're getting negative values of loss, which you always do. Right? You start at 0 or positive values at the central office, but by the time the light gets all the way down to you, it might be negative. Now, it should be positive, honestly. It should not have lost that much light, because we never put any of these hubs. I haven't seen a hub yet that was over 15,000 feet or so from a central office. Most of our feeders are fairly short, 20,000 at the most. I don't know what yours are. But if you have negative light at your hub, then you're already going to affect the input to that splitter, which is going to give you less light to the splitter. Okay? Go to the example that I saw this summer. We were sending a positive value of light from the central office. It was leaving out of the central office about a +3. By the time it got all the way down to the far end and we plugged into the actual feed fibers from the F1 side, we were like at a -5 or something. Now, the 1x32 splitters, and this is all this information, everything that I'm telling you, all comes from a standard. There's a certain standard, TIA 568, C.3, there's a D.0. There's a lot of different standards out there. When values, when I mean a lot of different standards, I mean a lot of different drafts or versions of standards, but most of the numbers, they're basically all the same. And when you go through this 32 dB splitter, you generally lose anywhere between 10 to 15 dB of loss. So if you already started a negative value, then you're going into a splitter that's already going to be negative value, then it gives you less light to your customer. The hub we were testing started at a negative value. Once it got all the way out to the customer, we were down past a negative 21, 22 at the house. There was not enough light for the actual photodiode on the network interface device on the house there to actually light up the house. What was the problem? We determined the issue ended up being that we had dirty connectors in the field. Now, who scopes these connectors? He takes an actual scope and looks at them. Raise your hand. Anybody do that? I do. I do. Anybody in here do? Probably not. It's okay. I'm not trying to call you out. Are they going to get in trouble for this? They're getting in trouble. Yeah. Boom. I need you to sign a document later that you test all this information. Legal affidavit. No one checks them with a scope, and I don't understand why. Majority of the connections were dirty. We cleaned them. I ended up scoping them. We did increase some of the value. Now, look, there were some other issues as well. I'm just going to be honest with you. There was a manufacturer's defect that was in there. There was a lot of issues at play. But we needed to not have that negative value before we went out to the customer. So if I want to see this last connection, I have got to put on a receive cable so the light can come out of there into another event, and then it may come down and then drop off. It's software noise. So if I truly wanted to analyze this whole thing, the first connection and the last connection, then until I put on a receive cable and I have the light go in and out of that last event, I can't move my cursor over here to the right-hand side to actually judge loss and distance across there. It's very important. All right, because at the end of the day, if we don't get enough light to the customer, then obviously we're not doing any good. Now, for today, I actually will be able to put on, I'm going to be able to connect this to receive cable, and then we'll do a shot across this again. And we're going to prove this and see that process. Now a little homemade number here. All right, we're going to go one more time. So we're going to go in. I'm once again not changing any settings yet. I'm going to change the settings here in a minute. But for now, I just want to show you running this in full auto. Am I still sharing at this point, or do I have to go back? Okay, that's cool. I think I understand now. Okay, and then what do I do? Share screen. Got it. Okay, and I am sharing. Very good. Okay. Everybody with me so far? What happened? I'm not really used to no one asking questions, so what? The heck? Now we're going to have a technical problem. Guys, do you not have any questions so far? Is that what you're telling me? What the heck? Go, let me hear it.
Instead of TDR can detect what you call a chromatic dispersion.
Mm-hmm.
You also said that it works off of the result. But does that dispersion cause reflection for it to be able to measure, or how does it measure chromatic dispersion? Questions.
So the way the back reflection works is it averages on time for how long it takes to get down to the event and return back. When you deal with chromatic dispersion, it's still a time factor for how long it takes the light to get down and return back at a certain wavelength. So yeah, I would assume it probably does. Now, I don't know that to be a complete fact because quite honestly, I've never checked for chromatic dispersion. I've never tested.
Hitting the fan is not,
Just losing power because of distance.
I had that doesn't cause reflection, that's just.
It should not cause any reflection at that point.
Meters set up.
Oh, you mean just chromatic? At that point, we don't even have a machine that tests for that. So I don't have one. I haven't used one. This is as far as I ever got with it. When you get into doing fiber characterization, it takes a totally different machine that's able to actually check at certain wavelengths and check over time and determine, all right, here's the wavelength I sent. Here's how the light appeared to have slowed. Now I know I have chromatic dispersion. I mean, also PMD, polarization mode dispersion. We don't check for that. I know that they're out there, never use one. That was a good question, though. I don't think in our world, nothing that we do is long enough. What the heck? You don't think I did what? I don't think I did either. Nothing in our world, stop that, is long enough for us to really see that issue. I'm going to be honest with you. Because when you get into links between cities, that's when it becomes an issue. Or submarine cables. So when I first was approached about coming, I think you're right. Thank you. What? It's not seeing the far end connection. And I'm not going to figure out what that is right now. Okay. So let's just bypass that for the moment. I'll have to figure that out. And then it's very silly to do that in front of you because I'll look stupid and it won't make any sense. But I was first approached. No. So, sure. We'll take a break. Sure. I just thought that'd be funny to say no. It's my show. I can do what I want. Sure. Yeah. I'll see if I can figure this out. But what I was going to initially say, and no one has, we'll talk about this. We were talking about EDFAs, erbium doped fiber amplifiers. You guys maybe you've heard about them. I hear you're using them. Maybe you deploy them. I don't know. Is this a true statement? Okay.
Mhm.
At the end user's house?
No.
Feeding the systems. Yeah. So erbium doped fiber amplifiers actually take, if you know how fiber is made with silicon and germanium. And they heat it up to a certain temperature, around 6,000 degrees, and that turns into what's known as silicon dioxide. That's how they make glass. Glass is so pure, so clean, so perfect that if we had a 2-kilometer piece of fiber right here and it was this window, it would look like I'm standing on one side and Jess is sitting on the other side. It would look to us as if we're looking at a single pane of glass. That's how pure 2 kilometers of glass is. Well, with erbium doped fiber, they use erbium to dope the actual glass. And so that amplifies the light. It's all passive systems. Now they do use some equipment in there to actually initiate the signal, but you guys are amplifying in the nodes. So you get pretty positive values. You get high values. Yeah, I bet it does. Positive above, I'm sure it's above 0, obviously it has to. I'm asking, I don't know.
To attenuate that typically.
Yeah. Well, that's cool. I had only heard that you guys were doing that. The only time I've ever seen them, we actually used them in the head ends. So it was actually how we pushed out the light. So
let's take a 5-minute break for everybody on the live stream. We're going to pause the video for a bit. Everybody in the room here, if you want to take a quick restroom break or grab a cup of coffee or something, go right ahead. And we'll be back in like approximately 5 minutes. I see 10:12 now Central on my watch. So roughly 10:17 Central. Thank you, folks.
all right, so let's get back into this. Now, when we just finished, I was going to show you with the TDR, we were going to look at how the trace looked different when I put on a receive cable. I have just put on a receive cable. I cannot, are we seeing this? We're good, sharing? I can't see past the last connector. I'm not going to sit here and waste your time to try to describe why I can't see past this. I don't really know right now, okay? And now is not the time to try to troubleshoot this right in front of me. But having said that, what we would have expected to have seen, let's close that door if you don't mind. I don't want to see anybody. Having said that, what I would have expected to have seen here is I would have seen another blip like this very first connection here. And I would have seen another one down there, and it would give me a little bit of distance to get out of that last connector to go into another piece of fiber so I could check the far end connector. Now I'm telling you guys procedures. I'm not telling you this is my opinion or what I feel like you should do. This is just what should be done if you really want to know the far end connector. Now, I will also have guys who'll ask me this next question. They'll say, well, all right, you know, we're never going to go out and put on a receive cable. You know, we're all from the world of production. Let's just be honest. Okay. The job is to light up the hub. We want the customers on as quickly as possible. If the connections aren't bad on the far end, do we really need to worry about it? No, I guess you don't. Okay. You can wait until there's actually a problem and then address the problem then. I'm not going to say that it's accepted practice, but it is kind of how it works, because generally speaking, when you guys go out and you're using nodes, you use nodes, but then nodes go to a hub, right? I don't know your network, but right. So generally speaking, these hubs are all pre-made at the factory. So when you get them, they should have already been checked, QC'd. So all the caps should be on them. So in theory, there should be no dirt or dust on them. So one thing that I was really a stickler for and came very close to wanting to just fire people was if I went to a cabinet that you just tested and you pulled all the blanks out so you could test, because it was just easier just to pull them all out and test, and you left them out, and I found that cabinet with open connections, I wanted to visit with you privately. Dirt, one speck of dust is enough to kill a fiber network. One speck of dust. So the next thing guys say, well, then how do you, there's no network that's ever going to work. I know that. I understand that. That's why I feel like you need to scope things. I mean, once again, I'll give you another example, real world example. I was helping some guys. I'll just say advising, whatever you want to call it. And they had a camera system. It was up and down, up and down, up and down. It worked for about 5 days and then it quit. And I said, well, you know, how are you cleaning? You guys are using the one clicks, right? The Cleatops or whatever. So I said, well, how are you cleaning? We're using the one click. What's the matter? Cool. So I discussed with them. I was like, well, you know, what are you doing to actually clean? I want you to scope them. Are you scoping them? No, we're not actually scoping. I said, so how do you know they're clean? Well, they didn't. All right, long story short. I showed them some of the proper methods, proper procedures, how to clean and then retest. And you obviously know how to clean, but I mean, if you don't clean and then check them, then do you really know if they're truly clean? They took a network that was like at a -25 and brought the power level up to about a -5. So dirt or dust is a very big deal. You walk out to these cabinets and you find those blanks open, there's a really good chance that there's dirt inside there. And that one speck of dust could kill a whole fiber network. So you do need to be careful. So that's it. So now that we've actually did a full auto trace, we see what the trace looks like. Let's just go ahead and talk a little bit about theory and how light works. All right. So just FYI for your information, light traveling through fiber is considered to be what's light inside a vacuum. What's a vacuum? Space. Light traveling in space travels about 300,000 kilometers per second. What they claim is, 186,000 miles per second, basically. Okay. Now, light in fiber travels at about 2/3 of that speed. So it's actually traveling about 203 kilometers per second. So That's why whenever we send light on this side of the earth, it immediately gets to the opposite side of the earth just that quick. So when we're testing our fiber networks, we're always testing a really short distance. This is another reason why you need to have a launch cable, because you'll never see the very first events on your network. If you even think that you can, it's impossible. Now, this brings me to what I tell guys whenever they're testing in the central offices at the head end. If going back to the example that I just had this week, if you're trying to prove that there is loss within 1,000 feet of where the machine is, you've got to use the launch cable. They had a loss at about 140 feet. Now, they didn't use a launch cable like I told them, so their trick was they just went to the far end and they shot it backwards and found out that it was inside the CO. But no matter what, don't forget to put on your launch cable. Needs to be at least 700 feet, as we said, 700 to 1,000 feet. Most of them, they say they're around 100 meters, 150 or so forth. Now, I do not know what standards that you guys use up here, but there are some companies that will actually require up to 3,000 feet for them to actually accept your OTDR test results. So you need to pay attention to that as well. One thing that I do talk about, this has truly nothing to do with testing, but it is something that you should pay attention to. Once again, this is a procedure, not an opinion, but these machines do need to be calibrated. I want to put it out there and say it, and it's not going to be good, but they should be calibrated annually. That's not really feasible sometimes. It's very expensive. Spend hundreds of dollars to ship the machines off. They're out of service for a couple of months. Then you get them back, and then you get a new calibration date. So you need to pay attention to that. If no one's arguing with you over your test results, because knowing that your machine hasn't been calibrated since 2016, 2017, then don't worry about it. Doesn't matter. Okay? Some companies do worry about that. So think about that as well. Now, we've made all these settings changes, but now I'm going to back it up. And unfortunately, we never got to see the actual unit where I could make the changes live. We're probably going to take another break. How long of a break would we end up taking? The next section. Okay, we may try to revisit this so that you can actually see. But basically, all that's going to change here as I start making these settings changes is the trace is just going to look a little bit different. So let's talk about the pulse width. And I'm going to go ahead and just write this on the board, and then we'll start here. We're going to go back to the world of theory. We'll come back to this here in just a second. Now, pulse widths start down to 1 meter. This one does 1 meter all the way up to 1,000 meters. When you think of a pulse width, it is a literal physical distance. It means that you left the flashlight on for a certain amount of time and it turned into a meter or 2 meters or 3 meters or so forth. So pulse widths, whenever you start out with a short pulse width, all right, let's say 1 meter, with a short pulse width, it will actually pick up quite a bit of anomalies on the fiber. It'll see a little bit of everything. But the shorter the pulse width, the less energy. Doesn't go as far. Now, the XFOs have an intelligent feature in them that when you set the actual distance of the cable that you're testing, then it changes the pulse width automatically. Because it knows when you're going to test a very long distance cable, you need to change the pulse width. So for the most part, you don't really make those changes. So if I'm going to test a short network, and once again, if I'm saying a short network, I'm going to claim definitely less than 7 kilometers. All right, so we're going to do 1 meter. We can do all the way up to maybe 100 meters for this 7-kilometer link. And it'll probably be just about the right pulse width. Earlier, I think, well, it says it right now. It says 500 nanoseconds. There's an equation that you can use that'll actually tell you how much the pulse width needs to be based off the distance of the cable. I don't know it by heart. I don't have it memorized, but there is a chart you can use, and it's like every nanosecond is a meter or something. Okay. Nobody's going to go that deep into the weeds on that, but just know shorter networks, shorter distances use shorter test pulses. The shorter the test pulse, the less energy, doesn't go as far. So as you know that the network is longer than a certain distance, and I can't say what exactly distance, the machine, if we were to dial that machine in, I would believe anywhere past 7 kilometers or so, it's pretty much going to say, hey, you need a wider test pulse. You need the distance, it needs to go further. So if we go with an actual longer pulse width, okay, let's say we're doing 500 meters or more. So we go to the long pulse width. Then at that point, now we're able to actually have more energy. We will see further, we'll get further distances. But what's going to happen in that actual trace itself? Like, look at are we still sharing the screen? What happened? Do I need to go back and yeah, hit me, boss. So when we get this shared, my apologies there, gentlemen. I don't mean to make you do that. Are we sharing now? Very good. All right, so you see the first connection. Now, you can barely see this connection right here. That's the one connected to the OTDR itself. That's a flat top, saturated peak. It's always going to be flat top. It's always saturated. It's overpowered. It's too much energy. The next one still has a flat top, has a pretty major reflective peak showing quite a bit here of loss. This one, it's not necessarily a flat peak, but it's not a good in and out. This one's still flat as well. It looks pretty bad. So, I mean, both of these kind of look bad. That just tells me that we pushed quite a bit of energy across there. So those flat peaks let me know that pulse width was a little wide. I could have dialed that down a little bit. Would have looked a little better, possibly. Now, look, we're talking troubleshooting right now. So I know the next thing guys say is, I don't ever really worry about that. I just want to know how long it is, and I want to find the bad fusion splice. I want to know where the fiber's broken. I want to find a micro bend. I know that. I understand that. I'm just trying to help you so you'll know kind of what you're looking at. So wider pulse widths, saturated peaks, shorter pulse widths gives you a better view of the actual OTDR trace itself, but it doesn't have as much energy. All right, so that's your pulse width. And when you go to range, you need to set the range to be twice the length of the cable that you're testing. Main reason for that is the OTDR needs to know that it left the light on long enough so that it found the end of the fiber. As I said whenever we first started, if you don't find the end of the fiber, do you honestly care? Not really. No, you need to analyze every single component. So when you set your range, let's say the network is 10 kilometers, the network we're about to test, then I would go into the unit and I'd say, all right, I'd actually set my range to be twice the length, so that obviously would be 20 kilometers. And having said all this, remember what I've told you before, a lot of guys, they say, well, we're going to run it in full auto. That's fine with me. I don't care. The only thing that doesn't change in full auto is you still have to determine the launch cable length. In full auto, you have to determine the launch cable length, or make those settings changes. So, and by the way, just FYI, I didn't even mention this earlier, but I'll go ahead and mention it now. I have a handout that I can give that shows settings changes, pretty standard stuff, recommended numbers. We'll share that with everyone. It's public knowledge. It's FOA material. It's not copyrighted, so I'll happily hand that out. So whenever I'm checking my network, I just want to make sure that the range is set to twice the length. All right, after I do the actual range, then I can actually do the averages, or what they call sampling. Now, sampling obviously is just what it means. It's how many times you send out a 1 meter, 2 meter, 3 meter, whatever pulse width to sample the actual network. Obviously, the greater the samples, the more information you're going to get back. But what does that mean? It means that it actually will change the test time and it'll make it a longer test time. Now, I'm going to go straight old school, if you will, and talk about what we do in the field. We go 5 nanoseconds, we go 1 meter test pulse, we go 5 and 5 sometimes, or we'll do a 30 nanosecond test pulse, 5 seconds on our averages. We do the shortest amounts we possibly can. Because when we're testing an 864 cable, it takes you 6 hours at least. 8 if you're doing it right. So obviously, the more that you sample, the more that you do your averages, the longer it's going to take you to actually get your network tested. For testing large networks, that's going to be a fairly big issue. When you're testing shorter networks, then maybe you would want to do that. Now, let me preface that statement by saying this: when I am checking my feeder route, that's a whole different animal than just checking my connection to the hub. Do you agree with that? It is, all right? Because when I'm checking the feeder route, now at this point, my feeder route is complete when I have attached every hub to that route. And now I know every single path that I will possibly have in the network. I take what's known as a fingerprint. Or I don't guess it's not necessarily known as a fingerprint, but normally a trace, that's what it is. It's an actual fingerprint. That way, when you start troubleshooting your networks later on, and you determine that you have anomalies, you have issues in the network, then you can go back to your original fingerprint and you can say, well, we had 15 hubs on here. It was 20,000 feet. These were the issues. These were anomalies. Now we have new issues. We got to break in you follow what I'm saying. That's it. 100%. So I just go back to my training and people I've worked with. I had a power company that deployed a system that's exactly what they did, is they did an OTDR trace of every single fiber that they ran, every feeder route, everything, and they called it their fingerprint. They stored it in a database. Then they ran a live OTDR trace across the fiber nonstop, every 10 seconds, across thousands and thousands and thousands of fibers. They checked the fingerprint against the live fiber, and wouldn't you know it, they were able to determine before the fiber was even going to break. It's known as health monitoring. As soon as they had a break, they initiated a lat and long coordinate that was a ticket that was sent directly to the technician. And sometimes he would get out there right as the event happened or just shortly after. But you could find the breaks quickly. Power company was very proactive in the fact that they knew if they had outages, they lose money. So they were ahead of the game. They were trying to stay ahead of what was potentially going to happen. So just to blow your mind, there's actually OTDRs that check sensors. There are sensors that can determine temperature changes. There are sensors that can determine gas. We use fiber on pipelines. Whenever the pipeline spews a certain amount of gas that comes out of, liquefied natural gas is, negative, whatever, 42 degrees or some nonsense. We run fiber on the actual pipeline. Whenever it changes the core size and changes the speed at which the light travels through that material, it sets off a sensor and says, here's where the leak is. So OTDR. So this is the smartest man in the room. Thank you, sir. That is an excellent question. So, and once again, I only know some of this stuff because of people I've advised and helped, okay? The amazing thing about fiber is, since we said earlier that we can send individual signals across one piece of fiber, we're doing it simultaneously. They don't intermingle or overlap. So we separate the wavelengths far enough apart, 1310, 1490, 1550. And then whenever you get into what's known as dense wave division multiplexing, we can put 64 channels. We can do 1550.05, 1550.10, 1550.15, 1550.20. You tracking with me? And they separate them by about a 0.5 nanometer wavelength. That light never overlaps or intermingles. Usually in my class, I bring in this fiberglass rod and I'll show you, and I can send 3 or 4 different light signals down one single fiber. As long as the wavelength is far enough apart from the other wavelength, it doesn't intermingle or overlap and create a whole new color. We transmit at 1625 and above just to test fiber. Because at the higher wavelengths, the longer the wavelength, the more it can see. Go.
Connector. What device is plugged into the pass the signal, the usable service signal, and shoot the TDR?
Man, it's a complicated switch at the head end.
Yeah, that's just, that's on my side of the house. We have like electronics in the, both the SFP or the QSFP.
Yep.
And the switch itself. I put it in components for the OTDR, so you can do that pulse at that unused data plane. Wavelength.
Yeah.
Be able to suck it back in the electronics and then forward it onto a server or a subscription service.
What's
Have
amazing,
to be built in.
that's right. And then what's amazing is he didn't describe the other really neat part, but I mean, there's like software-based OTDRs now that operate on these platforms, and they operate at the physical layer at the head end. And you're 100% correct. How does it do that? Well, it's constantly pulsing at these wavelengths. And as you said, you understand that completely, but how do they do that? That switch, that SFP module already has that capability built in to do that. So I'm just kind of showing you all the stuff the OTDR can do. It's very amazing. You know, some of the stuff that happens for security fences. We actually send pulses of light in security fences, and we also trench fiber and we put it underground. And we can determine if someone is stepping foot in an area just based off of a little bit of movement in the fiber. Just a little bit. It's absolutely amazing. So obviously, once again, going back to the settings changes, that's how we get more accurate information. If we constantly sample, then we're going to get more information. We're going to see a lot more anomalies on the fiber. The last thing that we would check would be our index of refraction. And then we'll actually do our wavelength. Now listen, when I talk about index of refraction, a lot of guys look at me like I'm crazy and they say they never actually make those settings changes and it doesn't matter to them. I agree with you. And I don't want anyone hearing me here in the class or anywhere else. I don't want you to hear me say, oh, every time you test, you got to change the index of refraction. Generally, the machines know what it is. Okay. They just do. They can automatically detect that. They send a pulse of light. It sees how far the light gets down. It sees where it bounces off the end. It averages, it determines, and it does this algebraic equation that says, here's the index of refraction. The only reason that this becomes an issue is real world example. We install fiber. You guys are installers, so you know this. You'll install fiber for a year and you may see 5 different fiber types. You agree? And then the project shuts down due to funding, and then all of a sudden you come back in the next year and then you install a whole new 5 different types of fiber. Now this will blow your mind and you will not believe me, but it is true. You look this up. Every fiber produced today will have a different index of refraction from a fiber produced tomorrow. Every manufacturer, because they don't all make the same glass. They don't use the same way to make glass. Their procedures are different. So occasionally you'll see what's known as gainers. Have you guys seen gainers? You ever seen a gainer? So when you're looking at the OTDR trace, all right, you got your initial pulse, you got this right here, you see your reflective event, and then you continue down. Well, normally if you see a fusion splice, if you even see it at all, if it's even visible, most of the time it's not, it'll just drop off just a hair and then it'll continue on. Do you agree with that? Just a little bit of a drop, just a little dip, not much. If it's a bad fusion splice, then it'll actually drop straight down. That'll show me that I got a little bit of reflection. But have you ever seen an event where you increased in your optical power and the light actually increased? It's known as a gainer. That happens whenever you splice 2 different fiber manufacturers together. They had different indexes of refraction on either side of that splice. So, having said that, knowing this information just kind of helps you to interpret the trace a little better when you're trying to find your issues. So, don't worry too much about that. I'm only speaking about it because we're doing a technical talk right now. The final thing that you would do is check all the different wavelengths that you're testing for. In our market, we actually test a wavelength of 1577. And different wavelengths that are totally foreign to some of you guys, and they're foreign to some of our equipment. If I check a network at 1550 and the network's transmitted at 1577, do you think that I might get an inaccurate test result? Well, yeah, slightly. I I've had Frontier and Charter and Time, who all these manufacturers, or not manufacturers, but installers and companies tell me that it truly does matter that you're using the precise wavelength. I do agree with that. That is true. But generally speaking, we have these wavelengths that we test with. So if you do see a wavelength that's foreign to your equipment, they suggest that you get a certain type of tester to really test with it. If that's really true, someone can correct me and prove me wrong. I've seen that the losses are negligible when checking with these wavelengths, but you do want to pay attention that you're actually checking the proper wavelength. All right. So let's go ahead and make those settings changes, and I'm going to go as full blast as I can. I'm going to overload this system. I'm going to increase my averages. And then we're going to run this in live mode. And then we'll dial it down. All right, and I'm still sharing, right? Very good. All right, when this finally wakes up. Wait a minute. Well, this is weird. I'm feeling kind of silly right now. Why? Earlier, I thought I had a way to view. Oh, I know. I got to close this. My bad, gentlemen. My apologies. I've got to close this and start it over. So it says I've stopped screen sharing. I'll look very good. Yes, sir. I will be back online any moment. Please bear with me. Come on, Al.
Hey, gang, while we're waiting, please don't forget on the live stream, if you have any questions, to post them in the chat room. Appreciate it.
All right. Looks a little different. Now, that was a complete exaggeration there. I was just trying to exaggerate. I don't know what happened. It's trying to exaggerate the settings changes, and now my laptop's going to act up on me. Here we go. So we have flat tops. Can't really see anything. The trace is nice and clean now. It's not as noisy. When you increase the averages, when you push more power, trace will look a little cleaner, will not have as much noise to it. Now, the main objective that I like to point out to this is you can actually push too much power and not see actual events that you're trying to locate. So it's kind of important to dial it down. Now, I couldn't show you this unit, but I'm going to just hold this up and we're going to display this real quick. I think everyone will be able to see this on the screen. The nice thing about this, we're seeing this, or we're still sharing the screen, aren't we? Very good. All right. The beautiful thing about this is I can make settings changes down here and I can do it in live mode. As I made those settings changes, then you would actually see as I'm doing this OTDR trace. So it's a little handier than this right here. So I'm testing a new network, trying to find an anomaly. I have no idea what's going on. I run it in what is known as real time. I started in real time. as it shoots in real time, then as it sees different events, they would see these events. I can sit here and change my pulse widths. I can change my range. And then I can change my averages. And as I change all that, it would change that view up there. Okay. And you can see it live. Now, a lot of guys don't want to do that. So then they can actually just come in here and set it in full auto. And whenever you do, then it asks you here to determine which wavelengths you want to test. And then you need to choose the ones for the network you're testing. So it's kind of a handier tool because now we're going to have to shut this down and start all over again. On this unit, another thing that's really nice is you can go in and make different changes here. You can come down and set this based off of a standard. You can set up what's known as thresholds. All right, so if your network allows you certain values of loss or reflection, you can put all that information in here, and then it will mark all of those events based off of your standard. Every splice loss is different for every company. I've had some companies that say 0.05 dB of loss is maximum per fusion splice. Some companies will allow you to have up to 0.3 dB of loss per fusion splice. But if you wanted, you can come in and pump all that information in here. I'm going to stop real time real quick. You can come in under the identification section, and this is probably where you guys are more familiar with. This is where you set up your operator. This is where you set up your fiber count. This is where you set up your fiber numbers, and it runs incrementally. So as you're testing, you start testing with fiber number 613, then your next fiber would roll over to 614, 615, 616, and it would put all that information in. So you can put that information in. You can set up who's the actual operator. Your test configuration is once again where you can set all of your parameters. This is what I was just telling you. Index of refraction. It shows you the different wavelengths that you can test. It will tell you maximum amount of reflection that you possibly could have. You could put in splice losses. Now, there's something really nice about some of these units that maybe a lot of guys don't know. You can just go in and pick the standard that your scope of work tells you to use. And then that standard will actually have all of the values of loss for a mated pair, loss across the glass itself, fusion splice, reflection, and different wavelengths. So, but some of these are very granular to where you can come in and make all those settings changes. Then you can come down into your user preferences. Here's where you are able to set either feet, meters, kilometers. See, this one's set in kilofeet. This is where you actually set where you do your saving of your test results itself. So whenever we start testing, the very first thing we do is we open up the machine. We set a file area on the machine for the project we're testing. And then we create a folder just to store all that data. Then we come into the preferences side here and we select that folder. Then we go inside those actual preferences and we say, all right, here's the fiber count, here's the fiber number. And in our world, it's FC731 is the fiber number, feeder number. And then we do the actual fiber counts. All that can be set in here. So this prints you a really nice PDF report. So it's very handy. That's why I do like these. They are very expensive, but they're very, very well functioning. You can save the results. You can open the results and review them. Something that a lot of guys don't know is you actually can produce reports directly on here. So and most machines have this feature. As soon as you get done, you can actually go in and you can select the report feature, and it will actually save a PDF report. So you can send it right off the machine directly. It's very handy. So I'll give you an example of why it helped me. When I first started doing work in the Indiana market, I didn't have a tech guy that was giving me access to the USB port on my machine. So I wasn't able to pull the actual PDF files off and make a report and blah, blah. All right. So I just went into the machine, made the report myself, turned it into a PDF, slapped it on a thumb drive, and then took it to someone who could send it in. So it's kind of handy. They also have new features now to where you can connect to Wi-Fi. You can set up an account on here and you can send the report directly from the field. Then they also have a feature where you can connect it to the internet. You can actually plug it into a Cat5 or Cat6 plug. You can manage this device on your own network. You can pull the files off directly and you can share it live while you're out in the field. There's a new feature now where you can actually share the trace while you're doing it. It's pretty amazing. So Exfo is, I'm acting like I'm an Exfo salesman here, but Exfo is kind of nice that it has that feature. All of these generally have a power meter on them as well, and then a VFL. This one has what's known as the IOLM. I tried to memorize that acronym and I've already forgotten it. So if somebody wants to look it up and holler it out, please do. It's like interactive optical light meter or something, light mapping. The IOLM feature, well, this is my opinion, so this is a secret, don't tell anyone, but the IOLM feature is for morons who can't read a trace. So there you go. Now, it's really, I do make fun of it because it is a dumbed down version of a trace, but the IOLM feature that's on here does actually allow you to see a full map of your network. It'll show you all your events. It'll show you your splitters. It'll show you your losses, and it puts it on an interactive map. That's kind of nice, I guess. I make fun of it because I grew up just looking at an OTDR trace, looking at a graph. Okay. So very handy. Here's something else I want to point out, just FYI for everyone. Do you know that these are color coded and why? Do you know that those ports are color coded and why? Because they only take APC connections. You cannot use, and it tells you right there. Yeah. I'm sorry, I keep moving. Let me get back to where I'm not moving. Now, let me tell you something. Never plug in an APC to a PC connection. That can damage it. All right. Now let me tell you something. Let me give you some technical information. This is not even on OTDR, but it's something I do want you to know. You need to know this. What is an APC? Does anyone know what it stands for? Angled physical contact connector. Every connector we use is a physical contact connector. All right. These are PC connections, physical contact. These right here are actually known as UPC, ultra physical contact. Just means that they have a dome top to them. All of our connectors do, they're not flat. Anyone tells you they're flat does not understand how fiber works. You got flat, you put another piece of flat on the other side, you got two pieces of glass sticking together. What happens? Reflection. So the connectors that we use have a dome top to them. There's a reason for that. You understand geometry, shapes. When you make a convex surface and you put a dome top, as the light comes down to the end of this connector right here, then all that light gets focused to the center, to what's known as the axis, and it comes straight out of the center. If you make this a flat top, then all that light comes down here and starts bouncing off the end face of the glass, and then has a problem connecting over to the other side. That's where reflection happens. So in fiber to the home, it's a very big deal to have back reflection. So we used what's known as an angled physical contact connector. Has a little 8-degree angle across the top of the connector. They're usually green. So as light travels down this fiber, when it gets down to this opposite end right here and it bounces off of this, where is the light going now? Since we've changed the angle of the glass, it goes back into the connector. It doesn't go back to the source. It minimizes back reflection. Why is that a problem? Enough back reflection in our networks will cause a problem with the source because that light keeps going back to where it was sent. Now, if you understand how fiber works, if you understand how light works, here's the most basic thing you need to know. And this will really help you. Light is energy. It's heat. It's an electric wave and a magnetic wave that are joined together at perfect 90-degree angles, and it travels in a corkscrew pattern down fiber. Anywhere, honestly, but that's how it operates in fiber. When you measure loss, you're measuring how intense that light is from where it started to where it ended. So it's always measuring the heat. So if you have enough light going back to where it came from, causes a problem. So APCs help to minimize back reflection. That's why we use them in all of our fiber to the home world. That's why it's used in all of our splitters. That's why it's used in your patch cords. And that's why no matter what, whenever you plug these in, you need to make sure that if that says green there, you plug green in. If it says blue, you plug in blue. There are other colors, by the way, so don't anyone, call me out and say, well, there's different colors. I've seen gray, I've seen slate, I've seen tan, whatever. I know that. I totally understand that. But in the fiber to the home world that you're used to, you're using blue connections because blue with a yellow cable or green with a yellow cable indicates single mode. Okay. So what we were showing here was actually what these connections look like. So kind of got a little sidetracked. So we'll come back to this now and let's finish this up. Now, oh, wrong one. I'm on it. Thank you, brother. Very good. Thank you. All right. So we want to now I want to get a little granular. And what I want to do is we'll change the settings one more time. And that might be the last settings change we make because we could go all day long. I could do all kinds of stuff to this machine and make changes to it, and it would look different every time. Which brings me to a statement that I've had a lot of students say. Well, it looks like to me you can just change the settings to make the OTDR look however you want. That's inaccurate. You actually have to know how to set it properly to get accurate information from your network. Now, can I fake this? Yeah, some people are dumb, unintelligent and don't know how to read traces. And I can probably do things to make it appear to look good. But me as an engineer and you guys as engineers, because that's what you're going for, that's what you need to be. You need to understand the technology you're working with. If I go in and I see those settings and I can say, oh yeah, I saw what he did right here. He used, one microsecond or 10 microsecond test pulse here. And he did more sampling and blah, blah, and he did all these settings changes and the trace looked better. Okay. So, you should know that just because you understand your machine. And then finally, just one last thing real quick. When you do your OTDR traces, you save your test results. And I'm sure guys will either admit to this or they'll say, yes, they've seen this or they've never really thought about it. But when you do save your test results and you do your actual OTDR shots, if you have bad back reflection at your cabinet, it will say that the network failed. Do you agree? Anyone that's done this, you agree? All right. Agree? So that only means that if you really wanted the network to truly pass, you probably should have went ahead and put on a receive cable at the far end. It definitely means there's something wrong with the far end connections, but it doesn't mean the network's bad. I had some engineers come to me and they said, oh, your network didn't pass. And I was like, what are you talking about? And I pulled up the trace and I looked and all they were referring to was it had a bad back reflection at the far end. I don't mean nothing. It was an open connection. I didn't put a connector on the end, so I didn't really check it. Now, when we went to put it into service, I might have had to go out there and fix it. And let me tell you, me personally, I like to be proactive than reactive. I don't like to do knee jerk. I want to be already prepared before I get there. Now, I know in the world of production, we don't always get to do that. But in that instance, it kind of messed me up because it turned into what was a no light issue. And then that no light issue I had to deal with. And then I had to go down and fix it. And then I didn't get paid for it because it's a long story. But the bottom line is if we went ahead and checked and had on a receive cable on the far end, that back reflection wouldn't have been there. The test would have shown up good. Because let's just be honest, some of these people want to see it either, green or red, So, all right, let's dial this in one last time and let's see what good and bad connections look like. I want to show you, I'm not going to be able to show you what it looks like going through a splitter. There's absolutely no way I can show you anything going through a splitter because the piece of equipment that I use doesn't push enough power to go through a splitter. You guys seen what splitters look like. You've seen how nodes will look and how they split. So it looks like a cascading effect on your trace. So you've got your OTDR trace, and you're looking at it, and you got your launch cable up here, and then you're going down the fiber, and then you'll drop, 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 and continue, and then come down and maybe see a reflective peak and drop off. Each one of these will probably be some type of a splitter, maybe a 1x8, 1x6, 1x4, whatever. But it'll slowly drop because every time you optically split a passive optical system, you lose 50% of the light or even more. So when you do look at these, you'll see the drops. And why is that important? Well, that could be a bad fusion splice. How are you going to determine the difference between if that's a bad fusion splice or if it's a splitter? Just off the top of your head, what would you do? I'm looking at this trace. I don't know what any of this is. I know that this is 4 kilometers to this distance right there. Okay, that's good. I'll do that. But I'm going very simple, and it blows past people because they don't. I'm asking a question that maybe doesn't make sense. But how do I truly know what that is? It's very simple. Documentation. That's right. That's why we started deploying a new system to where we have a thing called field maps, and we put all of our maps on a digital system, and then we map out our routes, and then that allows us to do checking distance. So if I start seeing that, I can say, well, at 4 kilometers, that's actually that's a split right there. I'm doing a 5-way splice, and I'm doing several laterals or off legs, and then right behind that, these are my actual splitters. These are my 1x4s, 1x6, 1x8, or whatever. So the main thing that I like to point out to guys as we do this and then as we test is OTDRs can be complicated. It gets even more complicated if you don't understand how it works, and then it gets even worse if you don't have proper cable documentation. Because you can chase light forever. I could give you horror stories of networks that we are in charge of now that was companies that I should not name their names. And they did things that were very, fast and loose. And when you're trying to chase a trouble, you could open, 10 or 15 cases. And if they're all aerial backyard easement, you're having a really good day. That's when you're super happy about your job. You're not rethinking your life choices. You're not thinking, welcome McDonald's, may I take your order? None of that's coming through your mind. You're on another pole. So it's very important that you know what you're looking at. Now, I've cleaned up the trace. It looks really good. I like it. This is what I would like to see. I'm still sharing, correct? We're good? Very good. And now I'm happy. I see a nice clean trace. I see my dead zone at the very first. I don't really want to analyze that. I don't care anything about this section right here. I care about from here forward. And I don't care past this because I don't have a receive cable on the far end. And now I actually can look, and do I see a bad fusion splice? No, I do not. Yeah, I know. You're seeing this right here? Now look, as I told you when I started, I don't know everything. When you do a shorter test pulse, it finds a lot of anomalies. So here's a fun fact. You're going to be smarter than the average installers. Fiber is in what's known an amorphous state. It's neither a solid nor a liquid. That's why we're able to fuse it together. You ever thought about it? How can you take something and break it, and then you heat it up and you fuse it back again? What did you do when you heated it up? What did you do to it? What did you do to the glass when you heated it up? That's right. You did. And you melted it. So after about 20 to 30 years, the glass begins to get brittle. Over time, it's going to break. It's going to get more solid. This unit will find anomalies with anything. I don't know what that is. It's inside this bare fiber spool. So I don't know. By the way, this is a little fun fact. No one's asked this, but what is this? This is a take-up reel. This is how fiber comes straight up from the factory. They can put 50,000, they can put 50 kilometers, 50,000 meters on one of these. That's how they make them. So that's kind of cool. I buy them direct from the factory and then turn them into test spools. So I don't know what that is. That answer your question?
Spool that's never been unspooled, and whatever it is, it's like some form of manufacturer variation.
That's right. That's right. Yeah. Now there's some broken pieces in here, and normally when I teach my testing class, I spend a lot more time on this, and we break this thing down, and I try to find out what's wrong, and I send red light across it, and we do a lot of stuff. We don't have time for that today, but I've had this thing for many years. It's become brittle, and it's just broken. So could be what it is. All right, the far end connection. The only thing I did kind of want you to see is what a good APC looked like. So what I'm going to do is I'm going to reconfigure all this real quick while we're in live mode. We're going to take this out of here, and I want to show you a good and bad connection. I'm going to show you what APC should look like. Now, this brings up another nice point that I like to point out. We've been testing this, believing that this link was 7,000 meters, 7 kilometers. Why now does it look so different? Why is it compressed? Well, let me throw something at you. This is once again, I get a little in the weeds because I like guys to understand what they're looking at. When you look at the mated pair, when we looked earlier at a mated pair, when we saw this connection, it looked just like this. And you saw a reflective peak. Okay. Are we seeing this one now? Are we seeing that? Very good. When we see a mated pair and we're looking at this, do you really believe that there's a couple of feet between a mated pair? There's no physical distance between the two. Well, the machine has to graphically represent this in such a way that you can actually see the event even happen. So it's known as the resolution. So right now, because we've been looking at a super long distance, when you look at this actual screen, then you say, oh, well, now the network's really short, and that's just this launch cable right now, and I'm only looking at 1/2 of that launch cable. That makes sense? So the resolution changes as the network grows and expands. All right. The APC on the end there, it really shouldn't look that bad. Honestly, it ought to look just about flawless. The reason that it does look bad, I have learned from, let me see which one I'm attached to. I've learned from scoping these that one of these connections is bad, and I just leave it in here because I use it as a teaching moment. But honestly, an APC, if you were to see a good APC, it would just go down and drop off straight, and it would have no back reflection, so it would just drop right off the cliff. So that one shouldn't have any back reflection. Now we're going to mate these two together and watch how this changes. It'll take it a second to catch up. That's fully caught up. Now, I need to go ahead and zoom in just to make this make sense. Why can't I zoom that in? Zoom. Oh, duh. I'm used to another system where you guys have probably seen it, you drag your window across there. All right, so here's my APC connection. Just made it. Now it's got a little dip. It drops, it spikes up, and then it has what's known as a baseline recovery. It has a baseline recovery issue. You see what I mean with the baseline recovery? We've got our spike right here. The APC looks fairly good. The connection's good, but then it just drops straight off like that. Why is that? The connection is damaged or something wrong. The mated pair didn't work well. Now, I left it in here as a teaching moment, but when I initially made this up, I didn't look at the ends to see that they're different. There's a different shape on them. So that's what that is. Flat top at the very far end, that's just because we're still pushing too much energy. And then we see something out here at the very end that's about twice the distance away from the end. That's a ghost. That's multiple reflections on short lengths of cable. How could you minimize a ghost? Well, we just need to, we need to either close down the light to this or we need to connect it into a receive cable. So you need to be able to spot those as well. I will say this connection right here, that's similar to what you could see if you saw a bad fusion splice, possibly. Well, it shouldn't look that bad. A fusion will just drop off, but you can see them look similar to that. Okay. And then the last thing I thought I would try to show is, let's see if we can see through a splitter. I doubt that we will, but I would like to give it a shot. So I'm going to send the signal down. And it's not even going to see. It's not. All right, so at that point, I know what I'm probably going to have to do, and I'm going to have to restart this. This is going to be very bad. I'm going to send the widest pulse I can, and I'm going to try to push through this thing, and possibly we'll see what it looks like, but I really doubt it. Okay, so just remember, if you do actually see those, you'll see it drop, drop, drop. That'll be basically what splitters will look like, if you do see them at all. I don't think we're going to see this one, by the way. All right, I got to change that. That looks terrible. Yeah. And I don't know. Yeah, it still looks about the same. I don't know exactly how some of these units actually push. Like the IOLM, it will do that. It has a feature that it pushes enough energy, plus it can determine when it is a splitter. So that's kind of why people use these, because you can go in and make a change on the screen and you can say, all right, I know this is a 1x8. I know this is a 1x12 or whatever. And then it'll actually see it. There's the splitter right there in the middle. And then all of it's flat topped at the end. And then the light just drops off. So I won't be able to see it. I'll try one more time. And then we'll give it a shot. This will be the last one. Yeah, see, it's still not going to see it. It does not determine basically what it does. I mean, it sees the first connection, then it's got that low baseline recovery thing. But the way that this works is when you're shooting downstream, then it should see all the little steps as it's dropping off the light. But in this device's mind, in the OTDR's mind, it's going to one single fiber, and then it's just going to one single fiber. So it doesn't really know which one it's connected to. We could probably put on here. I'll tell you what we'll do. This will be fun. I've never tried this, so let's see what it does, but I guarantee we'll probably see a little change in the light because then we're going to continue out of one of these splitters and go into another one. Yep, there it is. So now we've continued through one of the splitters. We're broadcasting through a complete 1x32. Now we've gone into a launch cable so we can see past that. So here, fun fact, we'll go do this. And I'll change this setting and we might actually be able to see now. But considering that it's passive, it's taking all the light through one individual location and sending it out 32 ways. So to it was just one. I'm not going to be able to see very well. It's not going to happen. Let's see, 10, save that. I'll try one more time and then I won't waste your time with this any longer. Yeah, it's not going to happen. I mean, it sees to the first event and then it just drops off and then it goes into the other one. So this is the launch cable all the way up to here. This is going through the splitter. It's dropping, which that's what it does. It drops this one. Last time we checked this, I believe we lost about 15 dB just going through that splitter, maybe 20. Well, that's what it's showing us. We're losing that much power. Well, when I push more power, I'll make a flat top to my far end connection and I may see the next connection, but it's still not going to go all the way. And if I'm making this complicated and this makes no sense to you, I do apologize because normally I don't like to just do things live and then try to figure it out. It confuses people. Yeah, we're getting a little closer. Now we're seeing a little more, but we had to push more energy, short distance once again. So now I see my launch cable, and then I see my connection to the splitter. It still dropped that much in power, and it is about 15 dB. So we dropped quite a bit. And then we have a flat top on the far connector. So it's proving that the splitter's good, it's showing how much loss is there. Make sense? So that's right. That's right. That's it. That's me attaching through my receive cable into that splitter. So now the light's going into one more path, and there we are. Yeah. All right. There's more that we can talk about. I need to show you one more thing that's very valuable and very important. Have you guys ever used what's known as a fiber identifier along with your OTDR? You ever use one of these? Huh? No? Yes? Maybe? Sometimes? What do you do this? What do you use this for? But all right, give me a little more. But you're on it though. You're on it. That's right. All right. This identifies live fiber. It has two little photodiodes inside there that whenever you push this up and you crimp this down, it will identify traffic. It's known as a traffic cop. Some people call them traffic cops. But out of our OTDR, we can actually send a tone, an audible tone across the fiber. And this will sit here and identify it. It's very, very handy. It's known as a tone generator, so to speak. I think I'll just use this. All right, so I'm going to disconnect this. I'm going to show you this. It's very handy. A lot of guys say, well, what would you use that for? The main reason that we use a tone generator is if we're out trying to identify a fiber, we use the live mode setting quite often, but if I truly need to identify a fiber, I can send tone across it, and that allows me to identify an individual fiber. Of course, I know that every fiber technician has one of these. You all have one of these, correct? Do you have one of these? You should. Where am I looking at? Where's my? Huh? It's right here. You get a free, you get this free bag with every OTDR course. Not. This is gender benders. All right, so we can test multiple networks. We've got a couple of devices in here that we use to test the head end. We can go to ST to SC. We can go to LC to SC. I've got attenuators in here as well to attenuate signal, and then I've got some that are just straight pass through. You should have, everyone should have one of those on their person at all times. And we're going to come over here and use this one. Will we be able to see this if we go like this? How do you want me to go, bro? Now, I know not the best way to do this, but you do need to see the different functions of this device. And all of your equipment has the same feature. Doesn't matter if you're using, you said Viavi, JDSU. They all have these features. So on the screen, you can actually see it has VFL power meter. That'd help. The reflection doesn't look great. Okay. Now, right now, I can actually send different signals. I can do the VFL to actually send light. And then I can come in here and I can set this to do different wavelengths. And I hope this does what I wanted it to do, because oh wow, it's not going to do it. Okay, I do apologize about that. So that is, that's my VFL. Bear with me as I see if I can find this setting. All right. If tools, I don't think that's it. Let's see. Utilities, that's not going to be it. I'm going to look in one more place, and if I can't find it, I'm not going to worry. Oh, I tell you what, I actually brought a backup. Always have a backup for a backup. I never do anything without a backup plan. Never leave home without a backup plan. This is a light source. This source is going to generate 1550 nanometer wavelength. It's going to send a 2 kilohertz tone out. This is about to give me this audible tone that I thought I could do over here. Now, a lot of times they don't let you know that some of these jackets you cannot see through. All right, here's the deal. What I'm getting at is the light doesn't actually come around. If you want to see this, the light doesn't actually get through the jacket due to the color of the jacket. Also, these are known as bend-insensitive fiber. Now, if you didn't know this, bend-insensitive fiber is used in fiber to the home all day long. It's every cable that we currently use. It's patch cords and it's aerial. It's known as G.657. It's a brand new cable. When I say brand new, I mean, 10 years maybe or more. All right. The way that it works is it compensates for any micro bends that you put in the fiber. So if I do actually try to check and identify a tone coming out of this, it might compensate for the loss that I've put in this cable whenever I put this on here, and I might not actually detect a tone. Okay. So if I don't shout me down because it didn't work, but it should see through this jacket. Now it'll see through all 250 micron fibers. We've proven that no matter what the color is. On your fiber identifier, which works hand in hand with the OTDR. That's why I wanted to show it. This is my OTDR's best friend. All right. I can actually change the heads on these and change the different types of cable that I'm going to test. And then I put this on here and I press up and I kink it. And it beeps. And then it tells me direction of the signal. And it'll actually tell me it's a 2 kilohertz tone. If I come in here and I change this, I can actually change my wavelength. I can come in and change this. So now I'm not sending tone at all. Now I'm going to send a really short tone. I'm going to send a 270 hertz, then a 1 kilohertz, and then a 2 kilohertz. And it allows me to identify the fiber. It's very handy. It's your best friend. Now, you've used it to identify if the fiber is just live. And that's awesome. But it is suggested that you use it to actually identify tone. So very handy. This machine should have done that. I don't know why it doesn't. I haven't played with this enough. I only played with this last night for a couple of hours. But normally they all have that. Okay. So that's a very handy tool. If it doesn't see through the jacket, that's just because the way that the fiber is designed, it's actually designed to compensate against you actually inserting loss in the fiber by kinking the fiber. So that's the last little tool that we like to work with in conjunction with the OTDR. And then finally, the very first thing that I ever use, no matter what I ever do, where I start personally is the VFL. I don't do anything until I start with red light. Now, if I were teaching this class the way that I normally teach it, then my opinion is I start with red light and I trace from that point forward. But look, I understand in the world of production that sometimes it's more advantageous for you to go out and shoot with the OTDR as soon as possible. So between those few items right there, and I do always carry a good light source to test with. I'm not going to make anyone do that. That's just me personally. I do that because we've had several issues in the field where our light sources had issues, and I just carry one out, a known good light source, so I can check my equipment against a reference, basically. So, like, I'll give you another real world example. We pulled a brand new patch cord right out of the box, the amphenol cables, the OptiTap ones, you know, the black ones that you screw in, they're APC connections. We pulled a brand new one straight out of the box, just used it one time and started to test. We went to set our reference. We couldn't set a reference. Well, to make a long story short, if we had started with the VFL, we could have sent red light across. We would have determined that there was actually a break in that cord, and then we would have not wasted our time. So I always start with the VFL very first. All right, that's about all that I have, at least at this point. There's some more that we could discuss. It's at a good breaking point. I don't know what our time is, by the way. Yeah, so I did not bring in a book that I wanted to, but I felt like it'd be silly to promote someone's material. But there's some really good reading on OTDR. My opinion is you need to look up a couple of reference guides and study the functionality of the OTDR. You really should. There's so much more that we could have gotten into. So there's some good reading out there that would help you to be more well-rounded, so that you could understand what you're doing a little better. So definitely do that. I still study. I go out and teach and still study. So that's just me. All right, that's about all I have. Any questions? There's not been one question. You've had a couple of good questions.
I don't know.
Go, let's hear it.
For people who are used to using NTDR, set the pulse width, if you set it too big, the section of cable you're doing, you can miss events. Correct?
Yes, sir.
The same thing can happen on an OTDR, right?
Yes, sir.
So you said that the pair-to-pair connection is a graphical representation comes up like that, right?
Mhm.
There's a break right after that pair-to-pair.
would it show up as a bigger loss on that pair to pair? Would you not see it graphically?
You might not even see it at all. It'd be too close. It's hard to see anything on the far ends. If the break is really close to where the mated pair is, it can be near to impossible to see. So what are you going to do then?
Shoot it the other way. That's why you shoot both
Shoot it the other way. And then final solution, VFL, red light. That thing will save your life. Yeah. But no, I've seen that happen quite often where it's right after a connection and it's within a few hundred feet. That's probably similar to what you're referring to, I would imagine.
Right.
And that's where our drop is. And from that point, within those few hundred feet, it doesn't even know it's there. Mm-mm. It is very simple, but it can be very complicated. I mean, you know, fiber is simpler than copper. Copper, you have 4 pairs. You've got to deal with shorts, grounds, splits, faults, corrosion. You got a lot of stuff. Impedance, power. You deal with fiber, you got one line, normally speaking. You guys are only testing one cable at a time, right? You're not doing any dual pairs for anything in this market, are you? Yeah, yeah. So, I mean, you just got to chase it down, chasing the light. A lot of fun.
Awesome. Is that all the questions in the room? Fantastic. There are no questions in the chat as well, so I
Oh,
think
my.
we're ready to wrap. We're good. Awesome. So Steven, thank you so much for being here. Really appreciate your time, appreciate your expertise.
Yes,
It's
sir.
been awesome. And if you folks have questions down the road, don't be afraid to reach out to Dennis, myself, Bob, Jessica, whoever on the Gateway chapter board. If you don't know how to get a hold of us, gatewayscte.org. We're a volunteer nonprofit organization, part of the larger 503c that is SCTE, a subsidiary, I don't know, how do you say the word? Subsidiary of Cable Labs. So the mission and values of SCTE is specifically promoting professional excellence, professional development, standards, and growth opportunities for the membership. The primary purpose of us is to serve the members. That's everybody on camera here, through the camera here that I can't see, and everybody in this room. Our purpose is to help grow and make things better for you, make the industry better. We do it a lot through volunteer efforts. We do it because we care. A lot of you have met me before and heard me before. For those of you who don't know me, my name is Hunter. I've been with Gateway Chapter SCTE since 2005. I've been in the cable business about 27 years, something like that. Been in technology about 30. For me, early on, my participation at SCTE and the Gateway Chapter Board was very much about what could I do for myself professionally? How can I make connections? How can I network? How can I learn more? How can I do more? At this stage in my career, it's all about giving back. It's literally the opportunity to give back because there were so many good people who served on the board and in SCTE. Some of them who are still out there today have been for 30, 40, 50 years in the business, who gave me a lot of opportunity, who lent an ear to me, who gave me advice. And so this is our opportunity as board members and people that contribute. Even Steven being here, he's not getting paid to do this. He's doing this because it's something he believes in. You can tell watching him. It's something he's passionate about discussing and sharing with people. It's about making it better for everybody else. So we really appreciate your participation, your attendance here today, your attendance on the live stream. We're going to post it to YouTube after some fancy editing. But again, if you have questions or something pops up later that you're curious, if you can't find it on Google, reach out to us. We will collectively be happy to funnel questions to Steven or to anybody else. So thank you so much for your time. Appreciate you. And we'll see you next time. Have a good one.